wait until the talk, so maybe if it's bad, you don't have to clap. All right. Everybody can hear me? Yes, good. Well, it's a pleasure to be here, to have a chance to give this talk today. This is a pretty crowded room. So this is work, as Mike was saying, that we...
I forgot to say. You should say that.
Yes, that's true. I was expecting you to say it. So I'm, well, I actually have a slide about this new affiliation. So I've actually just joined Google Brain in Montreal, so I've been there for about a week and a half now. Couldn't wait to come back to Alberta, so here I am. So it's quite exciting to see what's going to happen now with this new lab. What I'll present today is actually all work that we did at DeepMind. And as Mike mentioned, this is, of course, there's a lot of continuation of that's happening everywhere. There was actually a lot of questions as who is Google Brain and what are you doing in Montreal? So the Montreal office is actually fairly new. We're about 4 or 5 months old now, and right now we have 5 research scientists and three research engineers. They're at the bottom here. We're growing quite quickly. And basically we're doing fundamental research. So as with any fundamental research lab, we have a broad range of research interests. I'm being a bit biased here by saying we care about lifelong learning and also reinforcement learning, but we also care, program synthesis, convex and non-convex optimization, and deep learning in general. And we're quite excited. So we're very open to collaboration, very open to open sourcing our models, our RL and other algorithms. And one question I often get is, what's the difference with DeepMind? If you have questions afterwards, I'm sure we can have a longer discussion. But the short answer maybe is, we both do excellent research and we both do fundamental research. So let me start now.
You're different?
Did I say there was a difference? Let me start with sort of how this idea of distributional reinforcement learning came about. And I want to start maybe with an example. A game I'm sure many of you will have played called Monopoly, right? And in Monopoly, one thing that's often going to happen is you're sitting, for example, you're the wheelbarrow and sitting in Park Place, and somebody else is owning, owns both of these squares, and there's a hotel. You really don't want to land on Boardwalk. Quick show of hand, who's played Monopoly? Okay, that's reassuring. So basically, if we think of it in terms of AI terms, then we can imagine that two possible things can happen. Let's keep it simple here. One of them is you land on Boardwalk and you suffer this hefty penalty of having to pay $2,000 in rent. Or you skip Boardwalk, and then you pass go and you get some extra money. And the way we often think about this in reinforcement learning is we're going to look at the expected reward that's going to happen from this event. In this case, if you do the math, the odds of landing on Boardwalk are pretty slim. So the expected reward is actually positive, $139. Okay. So that's fine. Now, of course, the reinforcement learning problem is actually more complex than just looking at a single prediction, the immediate reward, but we're actually going to look at the number of interactions going forward into the future, at different places, right? And we're actually going to look at the sum of these rewards and discount them as we encounter them. In each of these rewards is going to be random in some way, right? So how do we do this in reinforcement learning? Well, the traditional approach is we're going to look at the value of a state X. And we're going to say that value is the expected sum of discounted rewards that's accumulated along the way. If most of you are taking the ARA class right now, then you know what this is about, right? And so, one of the tools we often use in reinforcement learning is we look at this sum of rewards and we just write it down using Bellman's equation to, in a concise form, where we say the value is actually the expected reward plus the discounted expected next state value. Okay. And we can do really cool things with this, like play Go to superhuman level, right? Now, the way this work came about was sort of a realization that under this game of Monopoly, or more generally speaking, the reinforcement learning problem, there's actually a lot of complexity. So if you look at a single rollout of a game of Monopoly, then the returns you're going to see are going to be very complex. And the actual distribution of them is going to be quite maybe multimodal. So one thing that's interesting, and I don't want you to get hold up on this, but it's an important point to me, is that if you look at the expected return, it sort of hides this intrinsic randomness. Okay? So in particular, this 139 expected reward, we're never actually going to encounter it. So when we model the expected return, we're not modeling the part of reality. Okay. So 2 years ago, Joel Viness, who was also at the University of Alberta a few years ago, Joel Viness and I started looking at this idea called compress and control. And this is where a lot of this work I'm going to be presenting today comes from. Okay? So the idea of compress and control was to say, if we look at the value function, it's an expectation, the sum of rewards. Okay? And zpi, you can think of the sum of rewards as a random variable. Okay? Well, if it's a random variable, we know we could estimate it using Monte Carlo. Right? So what does that mean? That means we do a rollout, look at the outcome, the sum of the returns, the rewards, sorry, and then that defines a target. So then we could do supervised learning to learn the distribution of all these returns, right? So that's what we did in that paper. And in fact, what we did is we said, let's assume that the return, the sum of the rewards, has a finite horizon of length m, and let's assume that it's undiscounted. And we did this so we could actually have a sort of tractable supervised learning problem. Now we have a number of possible outcomes, and we can just predict all of them. Okay. So this line of work has sort of gone back to this idea of looking at the random variable, but taking a completely different take. Okay. So we have this Bellman equation, which says that the value is the expected reward plus the expected next state value. Okay. And what this work is about is basically removing the expectations. Right? So if there's one take-home message here, that's what this work is about. Let's remove the expectations from the Bellman equation. Okay. Now, of course, the two questions are, well, what does that mean? And what can we do with it? So the first answer, sort of after digging through the math literature, we came about some work on recursive distributional equations, right? So how do we describe the relationship between a random variable on the left-hand side and a random variable on the right-hand side of an equation? So let me give you an example from actually the paper, the Rossler 92 paper on recursive distributional equations. And so it says, suppose you have a random variable x that is distributed like a sum of two random variables, x1 and x2, and we both weight these by 1 over square root 2. Okay? And let's assume, this is the recursive part, let's assume that all of these random variables actually distributed the same. So I'm looking for a random variable whose distribution corresponds to that equation. Can anybody guess the answer, what that x is? I'm going to give you a hint, first of all. There is an x that satisfies this equation. Any guess? No guesses. It's a normal distribution. So the normal distribution is actually the solution to the recursive distribution equation on top. Right? So that means if I plug this normal 0, 1 at the top, and I look then at the resulting distribution, it should look the same. Don't take my word for it. Read up the paper. Okay, so now we as the starting point, we said, well, okay, if we have a distributional Bellman equation, it's going to look like this. It's going to say there's a zpi, and the zpi is distributed like a reward plus a discounted other zpi at the next state. Okay. The picture sort of looks like this. You have a value distribution at a given state A, and I'm going to now transition to one of the two states, possibly receiving a reward. And I look at the two distributions that occur at the next time step. Right? And I'm saying if I were to look for the fixed point of the equation, that would be the one where nothing changes once I apply this equation. Okay. All right. So. Well, what does that mean? And didn't we know this already? Didn't we know that there's actually a fixed point that solves this equation? So some of the results that already were in the literature when we started working on this were, well, we know that, of course, the Bellman equation we know is the one that describes the relationship between one mean and the other mean. So we can at least describe this. There's also work giving an equation for the variance. So if you have the variance, the value function at the variance of the return at one state, then you can describe it in terms of the variance of the returns at the next states. Okay. There's also work on looking at these kinds of equations for Bayesian uncertainty, where now we're going to have a prior on what the value function looks like, and we're trying to quantify our uncertainty about it. Right. So what we're showing here is something different, which is about the actual stochasticity of the system, and not our uncertainty about the system. Okay. And there's actually more work about sort of Bellman equations for higher moments. What's different in what we're looking at here is we're actually trying to quantify the whole distribution all at once. So we're not actually looking at individual moments. And hopefully that gives us sort of a more unified perspective on things. Okay. All right. So whenever I write an RL paper, typically the first question I ask is there an operator I can look at? And an operator is basically a way of describing the expected behavior of your learning algorithm, right? So when we do learning and reinforcement learning, we're going to sample states from the environment. We're going to wander around the world and try to learn about this world. And one way to describe the average behavior that we get is by looking at the operator. How, if I do a one step of update, what's going to happen to my current prediction? Okay. So we can define an operator. We have a fixed point. So we know that there is a value distribution that satisfies this recursive equation. Now the question is there an actual operator that we could apply and use to study, if you will, the learning behavior? Okay, so I'm going to define this operator to be this, and we'll see what happens. Okay, so just to give you a sense for where the randomness in this process is coming from, in this operator that I'm defining here, there's really three sources of intrinsic randomness. There's the reward, right? So it's clear from the definition, T pi is my operator, and I'm looking at the result of applying this operator to a given value distribution. Okay. So I'm saying that the result of that update is going to be distributed like a random variable r, which is my reward, plus a random variable z at the next state. So z prime, z x prime, a prime. And I've sort of snuck in the actions now because I'm going to use the actions in a bit. Okay. So three sources of intrinsic randomness: the reward, the next state, and then what actually happens at the next state. If you're familiar with RL, this should look familiar, but also sort of, it's like the uncanny valley, right? It's almost the same, but not quite. All right, so let me sort of give you a picture view of what this equation is supposed to mean, okay? So we start with some prediction about the world, Z, and the prediction is a whole, it's a distribution at every state of what the return can look like. And the first thing we're going to look at is this applying this p pi z here denotes the next state distribution. We look at the next state and we say at the next state, the distribution looks like this. Now we need to learn about this distribution. So what we're first going to do is we're going to take that distribution and squash it with a discount factor. So all the returns actually move towards 0, right? And then the second thing we're going to do is we're going to add the reward, and that's going to shift it. And if you're familiar with distributional equation, you'll see that I'm being very sloppy here, because really what's happening is going to involve convolutions and not just shifts and squashes. But this is maybe a simpler picture here. So if you have, for example, two possible rewards, then you would convolve them with the reward function. So the way to think about this is that at the bottom, we have a target that we would like to predict. Okay. Make sense so far? Some nods? Good. Okay. So I'm setting this up so we can start talking about what it means to learn in this distributional framework. Okay. And to give you a sense, when we talk about the convergence of a reinforcement learning algorithm, we often talk about how it behaves as we repeatedly apply the operator, which describes this expected behavior. Okay. And the main tool probably that we use in RL is going to be this idea that the Bellman operator, the regular one, is what's called a contraction, which means that if we look at the distance between two value functions, Q1 and Q2, and we apply T pi, the operator, to both of them, they get closer together. Okay. And this matters because then what that means is if we repeat this process infinitely many times, then at the end of the process we'll have q pi, which is the fixed point or the target value that we're looking for. Okay, and you can see this because, so this is all an infinity norm, so the maximum distance between two state interactions. Because you have a contraction, gamma is a discount factor between 0 and 1. Because we have a contraction, as you multiply the gammas, they're going to go to 0, right? So at the end of the day, the norm has to be 0. So we can prove a lot of things with this technique. Now, the question is, what can we do with distributional RL? And the answer is, well, it's not so clear, because we can't just use that same infinity norm that we use in the regular case. The infinity norm is between two vectors, and we just look at the biggest difference between these two things. Okay, so if you're familiar with measuring distances between probabilities, you've probably heard of the Kullback-Leibler divergence. I'm going to start with two distributions, and I want to measure how far apart they are. So what's the KL divergence? Well, it's this formula on the left-hand side, right? It basically looks at the sum of the log probabilities and the log probability ratios, to be more exact. But there's an issue with the KL divergence, which is that if you have two distributions that don't have the same support, then it's infinite. So we can't have the same result that we had before in the expected case of saying that things shrink, because if you start with infinity, you're still going to have infinity afterwards. So the KL divergence doesn't work for us. Now, another metric that's very common in RL is the total variation metric, or sorry, not in RL, in machine learning. And the total variation is fairly simple. You have two distributions, and you look at how much probability mass do they disagree, right? So you subtract all the mass where they predict the same outcome, and you look at the difference, the mass of the difference, and that gives you the total variation. There's actually a paper already out there that showed that something like a distributional operator is a non-expansion in a total variation. So we don't actually, we can't grow the distance between distributions. Okay, but it turns out that's the best you can do, and here's why the total variation doesn't work either. If you start with two, so this is just a picture for just two distributions. I'm not talking about RL right now, but just two regular distributions. And I were to sort of shift them, so the distance to start with would be 1. If I now shift them, for example, multiplying by a discount factor of gamma, the total variation distance is still 1. So nothing's happened, right? So it looks like if we want to measure the distance between different value functions or value distributions as we apply this Bellman operator, we can't use this distance either. Okay. And so we come now to the Wasserstein metric, which we use in this paper. And I'll describe to you in pictures, so hopefully that's not too, that remains fairly light. So let me tell you about the Wasserstein metric. The idea is very simple. Who here is familiar with commutative distribution functions? Good, okay. So I'm going to take two random variables, u and v, and I'm going to draw their CDFs in red and green respectively on this plot, okay? And I'm going to look at the difference, so the area between these two curves, okay? And I'm going to define this to be the Wasserstein metric. So what does that mean? Well, it means we're going to start at 0, and we can think of it as integrating upwards, looking at all the differences, and that's going to be the distance between our two distributions, okay? And so if you want the actual equation, that's the equation at the bottom here. It's an integral from 0 to 1 of the inverse CDFs. But it doesn't matter too much. What matters the most is really, it's the area between the curves, okay? There's actually a generalization. It really doesn't matter too much, but you can generalize it to p norms to get a family of distributions. But we can only care about the first one. It's good enough for us, okay? So the reason why this matters is because we know things about the Wasserstein metric that are going to help us prove things about the reinforcement learning case, okay? So there's 3 properties. The first one is if I start with 2 random variables, u and v, and I add another random variable a to both of them, their distance doesn't increase, all right? The second one is if I multiply both of these random variables by a constant, well, the constant comes out, So I'm left with the absolute value of the constant outside of the equation. That's property number 2. And the last one is if I multiply by an operator A, think about a matrix, for example, then again the norm of that matrix is going to come out. Okay. So those 3 things together are going to help us prove the RL case. Okay. So I'm going to define a maximal Wasserstein metric, which basically says I'm going to give you 2 value distributions. And I'm going to look at the largest Wasserstein metric between any 2 pairs at any state in action. Okay. And then using this, here's the proof, but really it's very simple. You just use 1, 2, and 3, and then you're done. So using these 3 properties, we actually get that if we look at the Wasserstein metric after applying the Bellman operator to 2 value distributions, then we're going to end up with something which is at least gamma smaller than the original distance, right? And remember, this matters a lot because we don't have this with all the probability distances we could use, right? So there's something special about the Wasserstein metric that makes this work. And if you want more references, I'll be happy to provide you with them. Okay, so that's the first thing. Now, that's what we call the policy evaluation setting. We fix the policy, and we look at what happens as we look at the learning process, always applying this Bellman update 1 step at a time to using fixed policies. The other big case in reinforcement learning is the control case. We want to learn about the optimal policy. So in the usual sense, what we do is we replace the Bellman equation. Instead of choosing an action according to the policy pi, we're going to choose an action according to the max at the next time step. Okay. I realized I didn't talk about policies earlier. So policy is a way of choosing an action in a state. It's a probability distribution. Gives you the probability of choosing an action A, given that you're in a state X. Okay, so that would be the control case where we just choose the max. We're trying to get the optimal value function, which would be the maximum I can achieve if I were to choose the right actions in this domain. Okay. So a natural thing to do if we look at these distributions, these value distributions, is to say we're going to apply some sort of operator corresponding to a greedy choice. We're going to choose the policy such that we're greedy, so we maximize the expectation. We try to maximize the expected return we get. And unfortunately, we can't actually derive the same kind of results we had. So in the regular case, all the same proof techniques go through. We would have this infinity norm contraction, and then we could then conclude that we're going to converge to the optimal value function. And that's not going to be the case in the distributional setting. Okay. So just for fun, in the paper, we sort of gave a bunch of propositions saying really none of the things you might expect of this control operator hold. And I can sort of go over them very quickly, but the basic idea is that we don't have a contraction anymore. So we can't guarantee that we converge using the same proof techniques or the same, there's not the same process that's happening in here. Okay? And I'll actually give you an example in a second. We can prove convergence, but the convergence is going to be to a non-stationary optimal value distribution. So what does that mean? Well, as you're trying to learn about this optimal value function, optimal value distribution, you're going to make choices. You're applying your learning rule. You're going to make choices, choosing the action based on the greedy policy. And that choice is going to change based on your own guess. And as a result of that choice changing, I can actually show you that you converge to something that isn't described by any policy that would be stationary, that is, doesn't change its, how it chooses based on time. Have I lost everyone now? Yes, Rich.
Well, you're talking about the optimal value distribution.
Yes.
Is that defined?
I don't have the definition here, but I can define it for you if you want. So let's define the optimal, well, an optimal value distribution, because there's actually more than one, so that's a good starting point, as the value distribution of an optimal policy.
What's an optimal policy?
What's an optimal policy? So an optimal policy would be a policy which acts, so chooses actions so as to maximize expected reward. I apologize, I didn't put the definition in there.
It's the usual notion.
Exactly, you're right. So it's exactly the same notion of optimality as before. We haven't changed anything, except now we're learning about, it's a very good question, we're still learning, we're still acting according to the expected value, but we're looking at the behavior of this whole distribution as we do this learning process. Dale at the very back.
Sorry, I want to pick on the same point. Can you pass me a slide?
This slide.
Yeah. So not all optimality. So Rich says here's one. You said, yep, that's a good optimality operator. Then the elephant in the room is, does that optimality operator have a fixed point? Yes or no?
So your question is, does that optimality operator have a fixed point? Which that? Which? No. So I decided to not be as formal as I could, but maybe let me bring him. So we start with an operator which has to pick a greedy policy. Okay? So it has to choose a policy which, according to your current guess, chooses the maximum expected value. Yeah? All of these are optimality operators. As in, all of these are. So now the question is, how do you choose your greedy policy? You could either say you have two actions which have equal value. There is a decision to be made here. Right? I could always take action A, or I could always take action B, or I could have a mixture of any of them. And all of these will be greedy with respect to the current guess, because they all have the same expected value as predicted by your model. Right? So then you have a family, in a sense, you have a family of possible operators depending on how they choose. So you could say I order my actions and I always choose left. Yes.
Do any of them have a fixed point?
Yes. If you if you have a total ordering on your actions, you have a fixed point, and it might still be non-stationary. Sorry, you have a fixed point, but you might not converge to it. Because what's going to happen, and maybe we can take this offline afterwards. What's going to happen is, as you're making those choices and trying to converge to something, you're still making a guess. And you could still flip back and forth between two choices, which ultimately are optimal. Does that make sense? So things are actually quite messy. That's the short answer. You can't get away from it. Any other questions? Let's go to the example. So this example is actually going to try to illustrate some of these issues. It's very simple. You have a state x2 where you can choose one of two actions. You can choose action A1 and you receive a reward of 0. Or you can choose action A2 and receive a reward of ±1 plus a tiny epsilon bonus. Okay. So if epsilon is greater than 0, then that's a better action. That's the optimal action in the limit, right? Or rather, that's the optimal action. If epsilon is 0, then both actions are equally good from an expected value perspective. Okay. Now we started with this example, and I can use this whole example to basically demonstrate all the previous propositions, but I'll just give you one. I'll just show you the non-contraction, which means that you can get further away from the solution. Okay. So you can start with a guess about what the optimal value function is, which is very, very close. So you're going to say in state x1, which just leads to state x2, I'm going to predict that I get epsilon plus or minus 1. And if epsilon is greater than 0, that's optimal. You should always choose action A2 from x2. Okay? There's no discounting here. But now in state x2, I'm actually underestimating the value of A2. So when I apply my Bellman update, I have to be greedy. The rule is I have to choose the one with the expected value that's the highest. So I have to choose A1. Now, because epsilon is pretty small, Z and Z star, Z is my starting guess, Z and Z star are very close together. So the distance, you can imagine, I won't do the math here, but you can imagine the distance is very, very close. Now, when I do the update, I have to choose A1 at x2. It's the optimal action, according to my current guess. So that means that once I back up A1, I'm going to end up with a value called TZ, which looks like this. The value distribution after the Bellman update is going to have a distribution which is just a Dirac at 0. at x1, because x1 says my value is whatever I get at x2, and that's basically always 0. Whereas tz becomes, at x2 it becomes correct. And you can do the math and show that it's actually further away. Okay? What's happening here is that this Wasserstein metric I was telling you about captures not only the expectation, but all the other moments of your distribution to some extent. And even though you're getting closer in expectation, you're actually going further away in terms of variance. That's the sort of the simpler explanation. And so during the process of learning, the actual underlying distribution actually can change quite a bit. Okay? All right, so let me just give you sort of the picture. If we look at expected RL, we have a very clear picture where we start at Q0, a guess for a value function, and we can apply, for example, this Bellman operator repeatedly to converge to the optimal value function. If we look at the distributional case and we act greedily according to our expected value, then we're going to start at Z0, but we can actually get further before we go closer. And we're not even guaranteed to converge to the value distribution of an optimal policy. Okay, so that's actually quite surprising. All right, so in the interest of time, let me just keep moving with this and tell you about the actual algorithm that we derived out of all this new math. So the algorithm is called C51. Who here is familiar with things like deep Q networks, DQN? Is that roughly half? Okay, good. So DQN is a deep neural network architecture designed to play Atari 2600 games. Okay, and in DQN, we're trying to do reinforcement learning by having a neural network output the value function, so our prediction of what the value of an action is at a given state. So what we're going to do is we're going to replace that value prediction by a whole distribution. Okay. Specifically, we're going to output a discrete distribution with 51 possible values, uniformly spaced on an interval. Okay? And we're just going to use a softmax distribution, so exponentially or Boltzmann distribution to predict that thing. Okay? Now the key, if you have to remember one thing about this algorithm, is it's doing distribution to distribution updates. Okay? So we're really going to take the whole distribution next state and learn about that whole distribution, back it up to our current guess. And that's really, really important. Okay. So what we'd like to do is we have our picture from earlier, and we want to make this into a practical algorithm. So we're going to sample a transition. If we start in state X and take an action A and sample a transition, and then we compute a sample backup, which you can think of as a sort of a random operator, a sample backup. And then, of course, we've done all this math with the Wasserstein loss, or the Wasserstein metric. So we would like to define this loss and do, for example, gradient descent with respect to this loss. And it turns out you can't do this. And if I have time at the end of the talk, I'll show you why. Okay. So hopes crushed. What can we do? All right. Well, let's start over again. Let's start with, we'll sample a transition. We'll compute a sample backup. And then, what is one thing we know how to do, if I give you a distribution whose support is the same as what I'm outputting, I can always minimize the Kullback-Leibler divergence, the KL divergence. We know how to do this. It works well. Deep nets are very good at classifying things. So let's do this. Let's add a projection step, okay, where we first take the output of our sample backup and bring it back to the approximate distribution, so that discrete distribution we have, okay? And then that basically means, pictorially, we take the green output and we map it back to the space of things we can predict. And then we minimize the Kullback divergence between these two things. Okay. So that's actually what we do in the paper, the ICML paper. Yes, Rich?
If you only get a sample next state,
Yes.
so you really should have the distribution over the distribution.
Very good question. The distribution over the distributions.
Well, you're storing the distribution for each state,
Mm-hmm.
but you have a sample in the next state.
That's right.
So the equations seem to be referring to the p pi z, which you don't have. You don't even have a sample of p pi z.
The sample of p pi z. You do have a sample of p. So you have a next state.
Yes.
And at that next state, you have the whole you have your guess about that distribution.
The distribution of the next state.
That's right.
You know the distribution.
For all the next states.
Yeah.
That's correct. And that's why we can't minimize the Wasserstein directly, actually. But we can, what I'm going to claim is that we can, using a single sample, do unbiased, I'm not going to show you this, but we can do unbiased gradient, we get an unbiased gradient of the true objective by looking at a sample backup. So let's maybe, so if
If you move towards that sample backup,
yeah,
then you're not moving in the right direction.
you mean if you had two possible states, for example, that follow up.
Yeah.
But in expectation, you might hope that that we move in the right direction. So sometimes we move one direction and we pull some of the mass this way, and sometimes we pull some of the mass the other way. It's a very good question. I am not claiming that this is actually provably convergent. And it's actually a very interesting question to show that it is the right thing to do. It turns out that it is. I'm not going to talk about this today, but it turns out that you can actually show that this is an unbiased way of, this will learn the right distribution, if you will. Does that make sense?
The other thing I want to ask is, actually, you're only storing, presumably, you're not storing a whole distribution, you're only storing the histogram.
That's right.
And so I don't even know how that would be done, since the bins might not line up.
That's why we need the projection step. So that's why we can't minimize the KL divergence directly, because then we have infinite distances. There's nothing we can do. Once we do the projection step, we actually then are able to take a gradient in the direction of the target. The question is whether that projection is even meaningful. It is. And again, this came later, if you will. So Rich is pointing at the very last slide of my talk, which is going to show you a very nice picture of the theory on one side and the practice on the other side. And they don't really meet in the middle. And we've been working on this since. So just to sort of briefly move on with we can come back to the projection, but it's just a linear interpolation, basically, between, actually, I should tell you about this. So the projection is you get your target, and you need to map it back to the current thing. And to do so, we're going to look at every single atom in the target distribution and map it to its two nearest neighbors. What that means is you have, if we go back to this picture here, you have a number of bins as your target. There's a third picture. And for each of these bins, you're going to find the two nearest neighbors in your actual support to project onto and assign credit proportionally. Okay. I'll show you an example in a second of the actual the value distributions that you get. So we applied this C51 algorithm to Atari, to the Atari suite of games. And it was very surprising, actually, that so we tried with different number of atoms. If you don't have many, of course, maybe that's not obvious, but it doesn't work very well. As soon as you have sort of roughly 20 predictions or more, and there's good reasons for why this is the case, but about 20 predictions or more, things get better. And actually, with 51 predictions already, it was better than state of the art. So this was extremely surprising. We're also still asking the question, why is this working? But it does work. So we beat, we sort of handsomely beat the best competitor in a number of games. And at the bottom, you have actually comparison percentage improvements compared to an algorithm called double DQN, which was already quite good. Another cool thing is that if we compare to the DQN algorithm I was mentioning earlier, then we actually get to the same, but being better than that algorithm on 75%. We have 60 games in total that we're playing with, 60 Atari games, and we're better on 45 of them roughly after a quarter of the training time. So we're actually speeding up the learning process quite a bit. Okay, and here's a table. If you just look at it, sort of compulsory table of numbers, we are actually getting the state-of-the-art results, and it's quite exciting to be able to do this without any of the bells and whistles that were used in other implementations. So let me give you an example, show you a video of what these value distributions look like. So this is a game called Pong. You're a paddle trying to prevent the ball from going into its net, and the computer is trying to score into your net, and vice versa. Okay. So on the left-hand side, you actually have the game. You're the green paddle. On the right-hand side, you have the prediction made by the network after training. Okay. On the x-axis, you have the returns. Okay, so that's all the possible predictions you can make. And on the y-axis, you have the probability of each of these returns. Okay, and I'm actually coloring the different actions that the agent can take. And what you'll notice, and if you can see it, but when the actions matter, the distribution sort of neatly separates, saying, oh, you really should take this action now, otherwise it's going to cost you a point. Okay, so let me show you another example. This is Space Invaders, and there's actually something really cool that you're going to see now. So Space Invaders, you're trying to prevent the invaders from invading. And now in this game, so you see that the sort of the Gaussian shape is your average value, if you will. And most of the actions look the same, but there's enough information to make the right choice. Now, in this game, as the invaders come towards you, if they ever reach the bottom of the screen, you lose immediately. And you get basically a reward of 0, a return of 0 forever on. Now you're going to see the probability of 0 go up, as the model is sort of predicting that there's a small probability of actually just losing the game straight up. And you can see it happening now, right? So there's this nice bimodality of saying either I lose the game with some fraction of time, or I continue playing and I get my usual value. I think it's going to happen now. Let's wait and see. And you can see the color bar, they're higher, because the agent knows if I do this action right now, it's game over for me, right? So that was actually quite a neat result to see the value distribution sort of show this bimodality. Okay, that's what you sat all through the mat for, right? These videos. Okay, so you can sort of look at these distributions and you see all kinds of nifty effects. Again, sort of bimodalities. Sometimes what you'll see is, yes.
Can you explain why the agent didn't shoot the mothership?
Very good question. I didn't even see the mothership, but this agent that we use clips the rewards at, just like DQN, clips the rewards at 1 and -1. So the mothership has no extra value. It's exactly the same, apples and so that's probably the reason why. Any other questions? No? Okay, good. Okay, so one cool thing that happens with these distributions is there's actually aliasing in a system where sometimes the agent doesn't have enough information to predict its current state, and as a result, how much return it's going to get. And that happens in Pong, actually. And what you see here is you have two modes, which are actually showing you that the agent isn't sure if it has received the reward or not. And it's sort of intrinsic to this agent that it cannot tell these two things apart. Okay. I can come back to this if we have a bit of time at the end. Same thing in other games. And one interesting case is in a game called Q*bert, where if you jump off the cliff, you lose a life. And the agent says, that action is just a terrible idea. Just don't do this, right? Okay. So this is the picture that I was talking about earlier. I actually have a bit of time to tell you about the rest of the talk, so that's good. So this was the picture we would have liked to draw in our SCML paper. And the reality, as Rich sort of astutely pointed out, it looks more like this, right? We can't really use the Wasserstein distance to do the learning we'd like to do, so instead we came up with a heuristic that works really well. So let me tell you very quickly and in pictures where the bias in these gradients is coming from. Okay. This is actually, I'm going to now talk about work that we've done since trying to solve that problem. Okay. So let's go back to our cumulative distribution functions. We have FU, which is the first the CDF of a random variable u, and let's say that that's the actual target. So now I just have two distributions. There's no RL involved. I have theta star. That's my target. It's a Bernoulli distribution. So there's a single parameter that I need to estimate. Okay. Now I'm going to output v as a random variable with parameter theta. So there's an error here, and the error is, of course, the integral between these two curves. So it's the area between the curves. It's the shaded region on the diagram. Okay. So that's my Wasserstein metric, or if you want to see it as a loss, it's also a loss. If I take a gradient, the gradient says you're overshooting the parameter, bring it down. That's what you would expect from a good gradient descent algorithm, right? Okay. So now sort of coming back to Rich's question, what if instead of having access to theta star, the whole distribution, you just get to see samples from that Bernoulli distribution? So sometimes you get a 0 and sometimes you get a 1, according to the probability of the model. Okay? So let's start. We have our theta, which is our prediction. And sometimes we get a 1. And then we suffer this loss here, which is the shaded region here. And sometimes we see a 0. So the blue curve is actually the CDF for the sample backup, if you will, the sample distribution when you sample a single Bernoulli and you observe 0 or 1. If we observe a 1, that's the CDF we try to match to. If we observe a 0, that's the CDF we match to, and that's the error we get. Does that make sense to people? Right? So either it's too far, too high, or too low. So if you now look, basically this is going to be a loss. So if you look at this expected loss, you can draw this pictorially and say, well, that's sort of what my loss looks like. And if you stare at this for just a moment, you'll notice there's something worrisome about this loss, which is it's whatever your parameter theta is, it's going to fill up the whole box. It doesn't matter what your parameter is, the loss is always the same. Okay? And you can read the paper if you want for details, but in this particular case, actually that's not quite right. If theta is 1/2, then the gradient is 0, no matter what theta star actually is. And in general, the gradient will be biased. Okay, so that actually, very simple example shows you can't do SGD with a Wasserstein distance. And that's why we couldn't do what we wanted to in the paper. So let me just tell you about a solution. So let's go back to the Wasserstein. We have that the Wasserstein metric is we integrate in this direction, and we basically look at these intervals. And what we're going to do, so this is the Wasserstein 1. If we just take the integral, we can now squash these by a factor p. We take the power p to get a family of metrics, the Wasserstein p metrics. Now we could also integrate the other direction. Okay. And that is going to define, now we're going to take the same integrals, but now we squash by a factor p on the vertical axis. And that defines the family of LP metrics. It doesn't matter too much except to say that if you actually square the distances, that corresponds to a very special case called the Kramer distance. Kramer distance. This matters because it's not Kramer, but it's Kramer. So this Kramer distance ends up being really, really interesting. Okay. So remember we had these properties about the Wasserstein metric. Well, it turns out that there are more general class of what's called ideal metrics that you can sort of find in math journals from the USSR from the 70s. And it turns out that the LP metrics are contractions with a factor 1/p. All this to say, we'll have all the same magic we had before for the Kramer distance, but with a different factor. Okay? We also have that the gradients, as we take gradients, stochastic gradients, we won't have the same problem. Okay? So we can show this, which is not true for the Wasserstein metric. And what's interesting is that these unbiased gradients, where we sample a batch of data, compute the sample gradient, that's only true for p equals 2. So there's a very special magic case where if you take the LP metric with p equals 2, you suddenly get unbiased gradients and you can do SGD, and everything works out fine. Okay, so that's actually the end of my talk, and I'm going to end on an empty slide because it turns out that what I just described doesn't work in practice. And well, you know, there's many reasons why that is, but that's going to be for another talk. So I think I'm going to be done now and take some questions. So on this note, thank you very much. Please.